Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 30 on simple areas.
As we begin Chapter 4 of the course, we're going to turn from our classical tools of Taylor series, limits, derivatives, and integrals, and begin putting them to work. We'll focus on applications of the definite integral, beginning with some simple area formulae. We'll start small, but work our way up to bigger things.
You might think that when computing areas, there are a lot of formulae that you need to memorize. Well, fortunately, that's not the case. There's one formula that you need to know for area, and that is that area is the integral of the area element, dA. What do I mean by that? Let's recall some of the classical area formulae that you learned when you were in school. The area of a rectangle, or a parallelogram, or a triangle, or a circular disk. These you know, but do you know why they're true? They're true because they are the integral of the corresponding area element. Let's see how this works in a few examples. Recall a parallelogram. Now, you would probably argue by rearrangement that if you cut into pieces and reshuffle, then you can build a rectangle, and we all know the area of a rectangle. Well, that's good, but there's another way to think about this. Consider your parallelogram in the xy plane with the base on the x-axis, and then slice it into horizontal strips of, if you will, an infinitesimal thickness, dy. Then what is the width of each strip? It is, let's call it b, the length of the base of the parallelogram. Now, how do we get the area out of this? The area element, the area of this thin strip is, well, b times dy. Thinking of it as a rectangle with one edge of infinitesimal length. The area is the integral of the area element. That is the integral of b dy as y goes from 0 to h, the height of the parallelogram. And now let's see how it falls out. The integral of a constant dy is that constant b times y. Evaluate from 0 to h, and we obtain simply b times h, which we all know is the area. Now, there's a slightly different perspective we can put on this, namely that when we shear that parallelogram and slide the horizontal slices so that it becomes a rectangle, then we are not changing the area element. This shearing preserves the area element, and thus the area. That's a different sort of rearrangement argument, one at the infinitesimal level. This also helps us make sense of the area of a triangle. You're probably used to thinking of it as half the area of the bounding rectangle by using geometry and similar triangles, but we could do things a little bit differently if we also arrange this triangle so that the base is along the x-axis and shear it horizontally so that it becomes a right triangle. We see we have not changed the area since we've preserved the horizontal area elements. Now, the hypotenuse has the equation of y equals h over b times x. Now let's consider a slightly different area element, this one vertical. The height of that vertical strip is going to be, from our equation for y, h over b times x. The thickness is dx. And thus, computing the area as the integral of the area element, what do we get? We get the integral of h over b x dx as x goes from 0 to b. And now, what do we see? Well, h over b is a constant. X integrates to x squared over 2. Evaluating from 0 to b gives hb squared over 2b minus 0. Simplifying, we get 1/2 base times height. Very simple. The example of a circular disk finally takes us to a nonlinear case. The classical means for determining its area was to use an angular variable and to approximate as a limit of triangles. Let us do likewise. This is perhaps not exactly how Archimedes did it, but it's kind of close. Consider an angular variable, theta, and consider a wedge defined by an infinitesimal angle, d theta. Then, thinking of this wedge as approximately a triangle, not exactly, but approximately a triangle, to first order, what would the dimensions be? Well, we would say that the height of the triangle is roughly r, the radius of the circle. The base is going to have length r times d theta. That in mind, the area element is what? It is 1/2 the base times the height, that is r, times r d theta. The area, being the integral of the area element, is the integral of 1/2 r squared d theta, as theta sweeps all the way around from 0 to 2 pi. Now we know what? Well, wait a minute. There's no theta in the integrand. There's just r squared, which is a constant, as is 1/2. So we can pull out 1/2 r squared. The integral of d theta is, of course, theta. Evaluating that from 0 to 2 pi gives 2 pi times 1/2 r squared. That is pi r squared. The classical answer. Done very simply. But this is not the only way to do this problem. Consider if we used a radial variable and we sweep out thin annuli and fill up the disk in that manner. Let's call that radial variable t. The annular strip is going to have thickness dt, and now we need to argue that the area of this infinitesimal annular strip is the circumference, 2 pi t, times the thickness, dt. I'm not going to argue that that's really correct right now. Let me just state it, and let's see what happens when we integrate it. We get the integral of 2 pi t dt as t goes from 0 to r, the radius. That is, we get pi t squared as t goes from 0 to r. That again yields our answer, which, if nothing else, tells us that our area element was indeed correct. That is a very simple integral. But notice that it's not the only way that we can do it still. We can cut the disk into slices, let's say vertical slices, and we sweep from left to right. Placing the circular disk at the center of the xy plane allows us to use a strip of width dx and height given by what? Well, the equation of the circle is x squared plus y squared equals r squared. Solving for y gives plus or minus square root of r squared minus x squared. The area element, in this case, is going to be the height, that is twice root r squared minus x squared, times the width, dx. Then we see that integrating to get the area gives the integral of twice root r squared minus x squared dx. Evaluating the limits from minus r to r, what do we get? Well, this integral is not as easy as the other two that we've done. It is an even integrand, over a symmetric domain. So we could pull out the 2, double it, and integrate from 0 to r. But we're still not done. We would need to use trigonometric substitution, something of the form x equals r sine u, and do a little bit of work. I'm going to leave it to you to verify that what one gets for that integral is pi r squared over 4, leading to the final answer that we all know and love. Notice that depending on which way you split the domain up into area elements, the resulting integral may be trivial or maybe quite involved. This, then, leads to the example that we all know and love, the area between two curves, let's say f on the top and g on the bottom. Now, it's very clear, given what we've done, how to determine the area element in this case. Using a vertical strip, its height is going to be f of x minus g of x. Its width is dx. And so, integrating this, we see the classical formula that you've no doubt seen before. The area is the integral of f of x minus g of x dx as x goes from a to b. One interesting application of this formula is to economics, in the definition of something called the Gini Index. This is a ratio that is used to quantify income inequality in a fixed population. It relies on one slightly technical definition, and the rest is simple calculus. Let us denote by f of x the fraction of the total income earned by the lowest x fraction of the populace. The domain is x goes from 0 to 1, and you should think of x as a percentage of the population, and f of x as the amount of income earned by that lowest x percent. The Gini Index, denoted G, quantifies how far from a flat or even distribution the income is. What do I mean by that? Well, consider what this function f looks like. It tells you how much of the net income is being earned by what fraction of the population. A flat income would be the diagonal line where x equals y. Why? Well, the diagonal line would mean that if you look at the lowest 50% of the population, they earn 50% of all income. Of course, in practice, that's not true. They earn less. Folks at a higher income earn more and a larger percentage of the net income earned. The Gini Index is a measure of how far from the perfectly flat or equitable distribution you are, and it's defined as follows. It's the ratio of the area between the flat distribution, y equals x, and the true income distribution, y equals f. It's the ratio of that and the area between y equals x and y equals 0. Well, that denominator is just telling you the area of the triangle. And since the base and the height are 1, that's 1/2. So, another way to write the Gini Index is as the numerator, this area between f and x, namely x minus f of x dx, evaluated from 0 to 1, divided by 1/2, that is doubled. Let's look at this in a specific example. Let's compute the Gini Index for a power law distribution, assuming that income is distributed like a polynomial x to the n. Then, what would we get? Well, we integrate x minus f of x from 0 to 1 and double it. Well, that integral is almost trivial. It's going to be x squared over 2 minus x to the n plus 1 over n plus 1. Evaluating from 0 to 1 and then doubling what do we get? We get 1 minus 2 over n plus 1. Putting that over a common denominator yields the result of n minus 1 over n plus 1. If we look at a little bit of economic data, we find that in the year 2010, the state of New York had a Gini Index of 1/2, approximately. If the income in New York State were distributed according to a monomial, then what would that monomial be? Well, we see that it would be a cubic distribution. We can't conclude that, but if it were a monomial, it would be a cubic distribution. That's a nice application.
This lesson may have seemed a bit redundant. After all, you all know the formula for the area of a triangle or a circular disk. These are the classics. But by revisiting the classics, we deepen our understanding and make it possible to accomplish more difficult works later. That will happen in our next lesson when we consider more complex planar shapes.